All right. Today we're going to start diving into chapter 5. This section is on random variables and probability distributions. Um, Earlier on, I believe this was in chapter 1, we talked about what a statistical experiment and observation is. So, a statistical experiment or an observation is any process by which measurements are obtained. Uh, so, for example, counting eggs in a nest, measuring daily rainfall, etc., etc. And we often use the letter X. Uh, as a variable in mathematics classes, like pretty much everywhere. When we use the letter X to represent the quantitative result of an experiment, we'll call X a variable. This is where we get into the topic of what's called a random variable. Now, what is a random variable? A quantitative variable X is a random variable if the value that X takes on in a given experiment or observation is a chance or a random outcome. Okay. So again, if we're observing something through an experiment or an observation, okay, that quantitative variable is considered random if its value is from chance or from a random outcome. In addition to that, you have what's called a discrete random variable. So there are actually two types. Discrete is one of them. A discrete random variable, which is what we're going to cover, we're going to cover discrete in this chapter. A discrete random variable is a variable that can only take on a finite number of values or a countable number of values. Then you have what's called a continuous variable. A continuous random variable is one that can take on an infinite number of values, a countless number of values in a line interval. Now, what's the difference between the two? What's the difference between discrete and continuous? Well, it's pretty much exactly what we just mentioned. When we calculate a discrete random variable, it's normally the result of a counting. And when we count, like, for example, let's say we're taking a tally, right? Tallies are usually done using whole numbers, right? And usually that, here's an example, is counting the number of students in a math class, right? Those are usually done with whole numbers. It's impossible to have 25.5 students when using a discrete random variable. So discrete random variable is normally the result of a count, meaning that it's mostly illustrated through whole numbers. A continuous random variable is the result of measurement on a continuous scale. An example is air pressure in your tires, right? It's calculated by PSI. Well, PSI can be used or can be calculated as a decimal. And if you know anything about decimals, right? If you know anything about decimals, there are what's the technical term for it is uncountable. There are an uncountable number of numbers between any two whole numbers. Like, for example, 0 and 1. There's an uncountable amount of numbers between 0 and 1. All you got to do is just put another 0 after the right after the decimal point. That's what makes it a continuous random variable. So discrete is mostly whole numbers. Continuous random variable is mostly decimals, mostly dealing with decimals. Now, let's go through an example. Which of the following random variables are discrete and which are continuous? Measure the time it takes a student selected at random to register for the fall term. Now, how do we know if that's, how do we calculate that as either as discrete or not? Okay, well, first we need to discuss, we need to talk about, okay, we're talking about time. Yes, so how do I know if time can be considered a discrete variable? I need to figure out, well, okay, is time continuous? Like, can time be written out as a decimal, right? Can it take on any value? And reality is it can take on any value, right? Like, for example, I can say a student takes maybe 0.5 seconds to register for the fall term, or 0.5 minutes, I should say. Or someone could take maybe 3.5678 days to register for the fall term. So I can express time as a decimal. So that makes this a, there we go. I thought I had it. 1 second. Let's see. So that makes this continuous. So time is a continuous variable. Count the number of bad checks drawn on upright bank on a day selected at random. The answer is literally in the word, counting, right? And you can't have half a check. You can't have a quarter of a check, right? So this is a discrete variable. Measure the amount of gasoline needed to drive your car 200 miles. Well, we're measuring volume. Volume can take on any value. It can take on a whole number value. It can also take on a decimal value. Just pay attention next time you fill up your car with gas. Look at the gas meter underneath the money amount that you're paying for your gas. It's literally in decimal form. This is a continuous. This is a continuous variable. If it can take on pretty much any value, whole number or otherwise, it is a continuous value. It is a continuous variable. If it can only be the result of a counting, or if it can only be expressed as a whole number, then we can say that it is a discrete value, a discrete variable. All right, moving on. Random sample of 50 registered voters in a district. Find the number of those voters who voted in the last county election. That's literally a counting. That's a discrete variable. All right. Now we get into probability distribution. So we're not going to talk much about continuous variables in this chapter. We're going to focus on discrete random variables in this chapter. Now, a random variable has a probability distribution, whether it's discrete or continuous. Okay. But, well, first off, let's talk about what a probability distribution is. A probability distribution is an assignment of probabilities to each distinct value of a discrete random variable or to each interval of values of a continuous random variable. Okay? So here's what a probability distribution looks like. Okay? Here's what a probability distribution looks like. So, the probability distribution has a probability assigned to each distinct numerical value of the random variable. So when we look at a discrete random variable, or all the discrete random variables of a situation, right? In a probability distribution, every single one of those variables, or every single one of the values that can be assigned to that variable, has a probability. And what do we know about probabilities? The probabilities of each random variable has to be between 0 and 1, in decimal form, of course. And of course, you can convert it to percent form, but another way to say it is those probabilities are between 0 and 1. And because they're between 0 and 1, the sum of all probabilities that are assigned to that variable must be equal to 1. Okay? So each value, each numerical value of that variable, every value that that variable can take, has a probability assigned to it. It has to be between 0 and 1 in decimal form, and they all have to add up to be 1. So let's practice determining whether or not a distribution is a probability distribution or not. Okay? In a Pew Research Center poll, subjects were asked if the use of marijuana should be made legal, and the results from that poll have been used to create the table below. Here's your table. And so should marijuana be legal? It looks like 41% said yes, 52% said no, and 7% were undecided. Does this table describe a probability distribution? Well, what's the variable here? What's the variable here? The variable here is the responses in that poll. Now, what are the values that each of those that each poll has? Well, you can either say yes or no, or undecided. We're going to assume that those are all the three choices that were available in that poll. Do they have a numerical value attached to it? Yes, they do. Or does each value, we're going to call this a value, this a value, this a value. You can also, if it helps, you can also assign them a numerical value, like yes being 1, 2 being no, 3 being undecided. But in any case, for each of those responses, does it have a probability attached to it? Yes. Are those probabilities between 0 and 1? Absolutely. Now, question, do those values add up? Do those values add up to 1? Well, that's 0.41 plus 0.52 plus 0.07. 1 plus 2 is 3 plus 7 is 10. 1 plus 4 is 5 plus 5 is 1. Absolutely. Yes. So yes, this table does describe a probability distribution. Okay. Let's try another example. Some senior executives were asked when job applicants should discuss salary, and the table below is based on their responses. Does the table describe a probability distribution? Well, let's look at it. Does the table describe a probability distribution? Well, look, so number of interviews, or the number of interview, meaning that you had 3 different, I'm assuming that each of those numbers represents an interview that happened. Senior executive 1, senior executive 2, senior executive 3. But look at the probabilities here. I have 0.3, 0.26, and 0.1. So 0.3 plus 0.1, that's 0.4. 0.4 plus 0.26, that's 0.66. It's not equal to 1. So it's not a probability distribution because all of these probabilities do not add up to be equal to 1. All right, let's do one more example. A tool of cryptanalysis. So cryptanalysis is the science of code breaking. A tool of cryptanalysis is to use relative frequencies of occurrences of letters to break codes. In addition to cryptanalysis, creation of word games also uses the technique. Oxford Dictionaries did an analysis of letter frequencies in words listed in the main entries of the concise Oxford Dictionary. Suppose Langley took a random sample of 1,000 words occurring in crossword puzzles. The table on the next slide shows the relative frequency of letters occurring in the sample. All right, here's the probabilities in this table. So we want to go ahead and we want to fill those in. So these are frequencies of letters in a 1,000 letter sample. So if I'm going to fill these in, well, first off, I'm going to need to take the values that have missing probabilities, look at their frequencies, and divide it by 1,000. Because again, this is relative frequency here. So for A, 85 divided by 1,000, and that's 0.085. For 112, that's 0.112. For 75, that's 0.075. For O, that's 0.072. And for 36, that's 0.036. Okay. So first off, we need to make sure that all these add up to 1. So I'm going to go ahead and add all of these up. 0.085, 0.021, 0.045, plus 0.034, plus 0.112, 0.118, 0.025, 0.030, 0.075, 0.002, 0.011, 0.055, 0.030, 0.066, 0.072, 0.032, 0.002, 0.076, 0.057, 0.069, 0.036, 0.001, 0.013, 0.003, 0.018, and 0.003. And turns out it does add up to equal to 1. All right, so if a letter, clear this out, if a letter is selected at random from a crossword puzzle, what is the probability that that letter will be a value? Okay, so we're looking at the probability. I'm going to use, so yes, it does. Let's see. I'm going to use the rest of the space for this question. If a letter is selected at random, what is the probability that I choose an A, an E, an I, an O, or a U? Now I'm selecting one random letter. This is an OR probability, okay? Which, again, if you recall, we have to decide whether or not these probabilities are mutually exclusive. Can they happen at the same time? Well, I'm only picking one letter. So if I pick an A, that means I definitely didn't pick an E, I, an O, or U, and so on and so forth. That implies that these are mutually exclusive events. And again, this is an OR probability, so I'm using the addition rules. And because I'm using the addition rules, and because they're mutually exclusive, I need to find the probability of each one of these events. So the probability of A plus the probability of B, or not B, I meant E. Hold on 1 second. Yeah. E plus the probability of I plus the probability of O plus the probability of U. Okay. Well, if I look back at the chart, if I go back to the chart and look for those relative frequencies, right? So A, we said, was 0.05 or 0.85. I was 0.075. E was 0.0112. O was 0.072. And then U was 0.036. So let's add them up. 0.085 plus 0.075 plus 0.112 plus 0.072 plus 0.036. And I get 0.38 or 38%. 38% chance that the probability would be a vowel. Okay. Now, when we talk about probability distributions, just like probabilities of raw data, using raw data, probabilities of values in a probability distribution can also have a population and a sample. And again, these probability distributions can be thought of as relative frequency distribution based on a very large sample space, right? Which means it also has a mean, and it also has a standard deviation for both population and sample, right? Now, when we talk about population, right, y'all seen this before. This is the Greek letter mu. That's the value for mean. This is the lowercase Greek letter sigma that represents standard deviation. Okay? And then when we get to sample, x bar is the mean, and then lowercase s is the standard deviation. All right? So again, we're not just, so we're using the same terminology, but now we're going from values from a raw data sample or from raw data period to now values of a probability distribution of discrete random variables. All right? So when we calculate mean and standard deviation of a discrete population probability distribution, okay, then the mean is given using this formula. Now, I'm going to have to change this at some point, but I usually like to draw a bracket around these to demonstrate that I'm taking the sum of all of this. So P of x, so again, here's the mean. X is the value of the variable. P of x is the probability of that variable. Okay, and if I take the sum of all of those, there's my mean. Okay, and there'll be a step-by-step process that we use to translate these formulas. The mean of a discrete population probability distribution is also called expected value. All right, so anytime you hear the words mean or expected value, those are interchangeable. Those will mean the same thing. Okay. Then when we talk about standard deviation, okay, then we talk about standard deviation. Again, I'm going to preface this by putting a bracket around these two. Okay. Here's the formula for standard deviation of a discrete population probability distribution. Right? It's the square root of the sum of all square differences from the mean times the probability. And again, there'll be a step-by-step process that we can use to figure out, to translate these formulas. Okay. And even though it's called standard deviation of a discrete population probability distribution, we can also call it the standard deviation of the variable x. Okay. And again, in all of these cases, x is the value of the random variable, p of x is the probability of that variable, and the Greek letter sigma represents the sum taken for all values of the random variable. Okay. Now, the mean of a probability distribution, again, is also referred to as the expected value. And it's called the expected values because the mean represents a central point or a cluster point for the entire distribution, right? Like, think of it this way. Let's say you're watching a football game, and the football announcers talk about a quarterback's completion percentage. So that basically says that's basically an average percentage of, well, maybe not an average, but if they're talking about the average of or how about this? Rushing stats is probably a better example for this. Or passing yards. There you go. Passing yards passing and rushing yards are good examples of this. Let's say that the announcer brings up a quarterback's average passing yards for a season. Then it can be expected that the quarterback's passing yards for the game that they're currently playing will fall at or near that value. That's why it's called expected value. But when it comes to standard deviation, it's also represented as a measure of risk. Now, we talked about standard deviation as the difference or the spread of the data around its center, right? The larger the standard deviation, the more spread out the data is about the center. It's not as consistent, right? It's not as consistent. But the smaller the standard deviation, the more consistent, the less spread out the data is among the center, and that implies that if your standard deviation is large, it's very likely that your random variable is different from the expected value. But on the other side of that coin, if you have a smaller standard deviation, then that also implies that your value of x is closer or similar to that expected value. Now, enough talking about what it means. Let's talk about how to calculate it. All right, so here's how you calculate expected value. First, you want to identify the random variable and all of its values. What's the variable you're trying to look at? What are its potential values? You want to calculate the probability for each value, each of those potential values. Once you have that, you multiply the value of x, or each value of x, with its corresponding probability. Once you do that, you add them all up. The result is your expected value. When it comes to standard deviation, the first two steps are the same. Identify the random variable and all of its potential values, and calculate the probability for every value, every potential value it has. Here's where it deviates, pun intended. Then you want to calculate the average, calculate the mean, right? Calculate the mean. Then you want to subtract the mean from each value of x. You want to subtract the mean from each value of x. And again, this is all expected value. You need expected value to calculate standard deviation, okay? So once you have the expected value, then you subtract it from every value of x, okay? And similar to how we did variance and standard deviation of raw data in chapter 3, we're going to square each of those differences, square each result from step 4. Then we're going to multiply each of those results by that probability, by its corresponding probability. And then we add them up, and then take the square root of the sum, and then whatever's left over, or whatever you're left with, is your standard deviation. Okay. Let's look at an example so we can see what that looks like. At a carnival, you pay $2 to play a coin flipping game with 3 coins. You flip 3 coins in 1 round, and you win $1 for every coin that lands on tails. Are your expected earnings equal to the cost to play? So, in other words, is the expected value equal to this amount? Okay. Well, what's the variable in this game? Well, the variable interest counts the number of tails that show. So what is the sample space for the values of this random variable? Okay. At the same time, we're going to go ahead and count up the sample space while we're at it. There are 8 equally likely outcomes for throwing 3 coins in 1 round. All 3 of them could be heads. 1 of them could be tails. 2 of them could be tails, or all 3 could be tails. So let's go ahead. Let's complete this, right? So the only 2 that are missing are these 2 tails, 1 head, and all 3 tails. All 3 tails. They're your 8 outcomes. Now the variable is the number of tails that show, because that's what we want. Because you get $1 every time that you land on tails. Well, what is the sample space for the values of this random variable? Right? What are the possible outcomes for the number of tails that you get? Well, I could have 0 tails, like I did here. I could have 1 tail, like I have here. I could have 2 tails, like I have here. Ooh, hold on 1 second. I think I messed that up. Yeah. I could have 2 tails, or I could have 3 tails. So 0, 1, 2, and 3. 0, 1, 2, and 3 are my sample space. Now, how many times can that occur? How many times can that occur? What would be the frequency of that, of those equally likely outcomes? Okay, well, let's look at it using this chart. Let's look at it using this chart. So, for the number of ones, or for the number of tails, I should say, for the number of tails for your variable, if I get 0 tails, there's only one possibility that could happen where all 3 of them would be tails, right? Same thing for all 3 of them being tails. There's only one possibility, and that's all 3 being tails. But for the other 2, whether you have 1 tail or whether you have 2 tails in that round, they each have 3 potential outcomes, right? So the probability, these would have the same probability. Whoops, hold on 1 second here. 0.375. This would also have the same probability here. Okay, and there you go. Now, do those add up to 1? Let's find out. You got to make sure that it's a good probability distribution. 0.125 plus 0.375 plus 0.375 plus 0.125. And yes, it does add up to 1. We are good. Okay. So again, the variable represents the number of tails in that 1 round. Okay. 0 tails, that's heads, heads, heads. 1 time that can happen. 3 tails, 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 tails. Only 1 potential outcome that could happen, that could come from that. 1 tail, either heads, heads, tails, heads, tails, heads, or tails, heads, heads. That's 3. Same thing for 2 tails, right? Heads, tails, 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 heads, tails, or tails, tails, heads. Okay. Now, let's finish up this table by multiplying each value of x with its probability, okay? So, it's 2 times 0.375. That's 0.75. Sorry, I forgot to count this one too. 1 times 0.375. 0.375. And then, here, 3 times 0.125. That's 0.375. All right, so now let's go ahead and add these up. X, P of X. So I want to add these up. So 0 plus this plus this plus this. And I get 150. And again, this is the expected value. These are your expected earnings. So the question was, is the expected value less than, greater than, or equal to the cost of the game? Well, the cost of the game was $2. The cost of the game was $2. If your expected value is 150, that essentially means you're getting ripped off 50 cents. So no, the cost of the game is not worth the expected value that you get in return. So in all actuality, what does the discrete probability distribution tell us? Well, first off, it tells us the entire sample space on which the distribution is based. Gives you a look at the entire field on which you get your distribution from. It also tells us the corresponding probability of each event in that sample space. Okay? And again, we have formulas that tell us how to find both expected value and standard deviation of a distribution. Okay? And that's what discrete probability distributions tell us. Last thing I want to cover here in this section is on combining random variables. Right, so I don't have to deal with just one random variable. I can also calculate discrete probabilities with more than one variable. So if I have two constants a and b, and x is a random variable, then I can create a linear function of x with a new random variable called L, where L is equal to a plus b times x. Okay? And, again, just like before, these types of variables also have a mean. They have a standard deviation. And in this case, it also has a variance too. Okay? Again, we're talking about population still. Okay? So a linear function, L equals a plus bx, has a mean, a variance, and a standard deviation that's in those formulas. So the average, the expected value in a linear function is very similar to the function itself. Instead of a plus bx, it's a plus b times the average. Your variance is b squared times your standard deviation squared, if you're given the standard deviation. But if you're given the variance and you're trying to calculate standard deviation, again, just like we talked about in the past, standard deviation is the square root of the variance. But we do have to keep in mind that we take the positive value of whatever the square root of b squared is. Because remember, if you're solving an equation by taking a square root, you have to consider the plus or minus. But we're talking about measurements, so we're going to keep, instead of doing plus or minus when we take the square root, we're just going to keep the plus. So whatever the square root of b squared is, you have to take the absolute value of that. Got to take the absolute value of that. Okay. And then you also have, so that's linear functions of one random variable. What about more than one random variable? Here's where we get into linear combinations here. If there are two random variables, let's call them x1 and x2. And let's say these variables are independent. Okay? They're both independent events. Okay, then you have a new random variable called W, where if I take A and B as constants, any constants, A times x1 plus B times x2, that is called a linear combination of x1 and x2. And of course, it's also got mean, variance, standard deviation. Okay, and just like before, the expected value is pretty much the same as the formula itself. Instead of multiplying each constant by the variable, you're multiplying each constant by the expected value. So the expected value of W would be A times the expected value of x1 plus B times the expected value of x2. Okay, and you also get something similar for the variance. Okay, so you have A for the variance of W, it's the variance, it's A squared times the variance of x1 plus B squared times the variance of x2. And then you take the square root of that to find the standard deviation of W. So here's an example that we'll use to help us out here. We have two different variables, two independent variables, each of them having their own expected value and standard deviation. Norb and Gary are entered in a local golf tournament. Both have played the local course many times. Their scores are random variables with the following expected values and standard deviations. Okay, so Norb, his expected value is 115. His standard deviation is 12. Gary's expected value is 100, and his standard deviation is 8. Now, judging by the way the golf is played, and judging by the expected value and standard deviation, it seems like Gary is the better player. In golf, the scores are, it's the lowest score that wins. And if you look at his standard deviation, it's smaller than Norb's, which means that his scores are more consistent than Norb's. Just FYI. In the tournament, Norb and Gary are not playing each other, so we can assume that their scores vary independently of each other. All right. So let's answer the following questions. The difference between their scores is W equals x1 minus x2. Compute the mean, variance, and standard deviations for that random variable. So again, here's the random variables here: 115 and 12 for Norb, 108 for Gary. We want to find the expected value, variance, and the standard deviation for the random variable W. Okay. So looking at this value here, it seems as though give me a second here. If we're looking at the formula by itself by itself I mean the linear function, the linear combination function. It's A times x1 plus B times x2. If that is the case, then judging by this right here, it seems as though A is positive 1 and B is negative 1. Okay, so let's keep that in mind here. Okay, so we'll start with mean. We'll start with the average here. The average of W, the expected value of W, is A, in this case 1, times the expected value of Norb, which is 115, plus B, which is negative 1, times the expected value of Gary, which is 100. So that's 115, that's negative 100. That's 115 minus 100, that's 15. That's the expected value of the differences between their scores. Now let's look for the variance. Well, for the variance, we're going to take A squared, so that's 1 squared. And here we can use the relationship between variance and standard deviation, right? I have standard deviation for both of them. Norm's is 12. Gary's is 8. So it's 12 squared plus -1 squared times 8 squared, right? So 1 squared and -1 squared are just going to be 1, so we're really just calculating 12 squared plus 8 squared. That's 144 plus 64. That's 208. And we already know, and so we already know what the variance is, so we're going to go ahead and take the square root of that number. And if this were algebra 2, I'd tell you to reduce that square root, but we're not. We're just going to go ahead and calculate its standard deviation and round to 1 decimal place. Square root of 208, 14.4. There's my standard deviation. Okay. Now, let's change it up. Let's say the average of their scores is W times 1/2 x1 plus 1/2 x2. Let's go ahead and make that calculation. All right, so it appears that A and B are both 1/2, or 0.5. We'll go ahead and use 0.5 just because, why not? Average, or expected value, I should say. 0.5 times 115 plus 0.5 times 12. No, I'm sorry, 100. Sorry. 100. I was looking in the wrong way. All right, and here we go. That's 57.5 plus 50. That equals to about 107.5. There's the average expected value. That's the expected value of their average. All right, let's find the variance. 0.5 squared times... Actually, we already know what those squares are, so I'm just going to type in the square values. So 12 squared, that's 144. Plus 0.5 squared times 64. Okay. So 0.5 squared is 0.25. So it's 0.25 times 144, which is 36. 0.25 times 64, that's 16. 36 plus 16, that's 52. There's my variance. Take the square root of that number. I'm sorry, 52, not 56. 52, so take the square root of 52. Round to 1 decimal place, 7.2. So again, once we know what the standard deviation is, we can use that relationship between variance and standard deviation to calculate all that. For linear combinations, once I know what this is, I can just take the square root of that number. That is the standard deviation for the combined set.